Hi, my name is Laurent Itti from USC, and it's a great pleasure to be here. Thank you again to Vibhav and Yogesh and the other organizers for this great meeting. Today, we'll tell you about some algorithms for robust lifelong learning and also robust training when learning from sequential data. So to get started, let's consider the lifelong learning problems, which is something that we have already looked at today. So maybe, on day one, I want to learn how to swim. On day two, how to learn the bike, how to ride a bike. On day N, how to play the piano. And the main question when we are trying to do that with artificial systems is how are we going to not forget the task that we have previously learned? So this is a problem because each time we learn a new task, this tends to erase whatever we have learned from previous tasks, again, as we have already seen today. So to get started, recently we created a small taxonomy of different approaches to address this problem, which I'm going to briefly review. And then I'll tell you about a new type of approach that we have recently developed. So the first type of approaches, which is probably the most intuitive, is to try to constrain the weights to what we have already trained on previous tasks by the time we learn a new task. So here the representation is that we have a network and we first train it on some task, let's say here task T-1. And what we are going to do when we try to learn task T is we will allow all of the weights for all of the neurons to be retrained, but subject to some constraint that we don't want to change those weights too much, so that hopefully we will preserve performance on the previous tasks as we are also learning the new task. And the classic example of this is EWC by Kirkpatrick and colleagues. Another possible way that we can think of is to maybe extend the network. In this case, for example, we have trained a network on previous tasks, and when the time comes to learn a new task in red here, we can add new neurons and new connections, and the other ones are going to remain frozen so that we maintain the performance on the old task, and we are only going to train the new connections in order to learn the new task. We can either do this expansion with no retraining at all, so that part of the network is frozen, or we can also allow some partial retraining on the previously learned weights. And here are a couple of examples of that approach. A third type of approach is now not based on doing constraints, but on instead doing some replay or some rehearsal. And the idea here is maybe we can keep a portion of the training data from previous tasks so that when we learn from the data from a new task, we can then interleave that with some of the data from the old tasks and then learn from the combination of those two. When we do this, we avoid catastrophic forgetting because we are at the same time learning new things and also rehearsing the old knowledge that we had previously acquired. So I'll show you some examples of that in comparison to our results, in particular using GEM. Finally, one fourth type of approaches is using context or mask matrices to try to create some subspaces or subnetworks that are going to be carved out of a bigger network where each subnetwork is basically going to be trained for a particular task. In this representation, for example, we have a network and then we apply different masks to the outputs of that network. Some mask for this task and some other mask for another task. So in addition to those approaches, one approach that we have recently developed in my lab is to try to take inspiration from what we have learned from adversarial attacks and to try to do the same thing, but now in reverse, so as to provide a benefit for each task. The way in which we are going to operate this is by adding some out-of-network biasing units that are going to be task-dependent. So when we are learning task T-1, we are going to activate the blue biasing units here. And when we are learning or running task T, we are going to activate those red biasing units here. So what the biasing units are going to do is basically to set some small offsets onto the operating regime of the network. And that small offset is going to be task dependent. So note how here we are assuming that we are going to be in a framework where there is a task oracle. So when we are either learning or running a particular task, we will be told which task we are currently performing. So in this approach, basically we are going to first train the network, and we are going to do that in conjunction with another lifelong learning method. For example, that network could be trained with EWC. And in addition to this, we are going to activate those task-dependent biases. And the goal here was to try to get all the check marks here, to be parameter efficient, memory efficient, no requirement of previous data, able to learn multiple input to output mappings, and unlimited capacity to accommodate for new tasks. All right, so let me try to give you the intuition for how this is going to work. So here we are just showing as a function of the parameter space, plotting the loss. And here, for example, let's say that we first learn task A, and that may give rise to this loss curve here with the optimum parameter set here for task A. If we then want to switch to learning task B, if we just do simple gradient descent, basically this is going to switch us to this optimum parameter set for task B. Now, those parameters here that are the best for task B give rise to a pretty high loss for task A, right? So if instead of just doing gradient descent, we now do EWCT or PSP, we will end up in this compromise region here, which is basically a parameter set which is not really optimal for either of the two tasks, but which is pretty close, and so which is performing well on both tasks simultaneously. So our idea is to start from this point, which is pretty good, and then to ask, well, could we add some like small task-dependent fine-tuning, if you want, but we are going to just fine-tune the biases as opposed to fine-tuning all the weights of the network. And could we do that in such a way that we are going to, when we are running task A, we will activate the biases for task A, and that should bring us back here in this optimum for task A. And we are running task B, we want to activate the biases that bring us back to the optimum for task B. So the way in which we are going to do that is, again, by taking inspiration from adversarial attacks. We are going to run a reverse adversarial attack, if you want, where when we are running task A, the biases that we are going to apply are going to be trained using the fast gradient sign direction, but the opposite of it. So basically, we are when we are told that we are running task A, we are going to try to force the network into being really only caring about task A. And that will help with bringing us back into this optimum regime for task A, and likewise for task B. So the advantage of this is that we only need to learn a few biases, which typically is a very small number compared to the number of weights that we would have to learn if we wanted to do task-dependent fine-tuning of the weights. For example, if you take, say, an exception network, there is about 23 million weights, but there are only about 20,000 neurons in that network, and so only 20,000 biases that we need to learn. In the results that I will show you, we actually used even smaller network that had only on the order of 4,000 biases. All right, so this is the basic idea. We have a core network here and different sets of biases that can be activated for different tasks. So in this case, task A is in blue, task B in red. And when we learn the first task, we activate the biases that correspond to this task. We learn, we train the network, all the weights in the network using stochastic gradient descent. And at the same time, we use that fast gradient sign direction to learn the values for those biases. And basically, we are reinforcing the network into being highly performant on that task using those biases. When we are testing on task A, again, here we assume a task oracle. So we are going to be told which task we should run. and we are then going to activate the corresponding biases and then just run the network forward as usual. Now, when we learn task B, the idea is basically the same. The only difference is that now when we train the main network, so first of all, we activate the biases for task B now, the red ones. And when we train the main network, we are going to do gradient descent, but also apply some other lifelong learning methods, for example, EWC, in order to try to reach that compromise solution using the core network alone. And again, we are also going to learn those extra biases to help us add that little fine-tuning on top of what EWC would converge to. And then testing on task B is the same. It's just a regular forward pass. Just we activate the biases for task B. So this is how we are going to look at the results. Here as a function of time or the number of epochs here. We look at the accuracy on a succession of several tasks, in this case, 5 tasks. And here each task is pretty simple. This is on MNIST, where in the first task, we are just learning to discriminate handwritten digits, zeros versus ones. And when at the dash line here, we switch to task 2, and we are trying to now discriminate 2s versus 3s, and so on. So if we look at the performance on task 1, we can see that for all the methods tested here, they all, as we start training, they all perform very well and converge to almost 100% accuracy. However, as soon as we switch to task 2, the performance on task 1 starts decreasing for some methods, but it remains for other methods. So the methods that work well in this case are our proposed method, this beneficial direction for the biases combined with EWC. And also GEM, which is one of those replay methods where in this case, we kept a little buffer or episodic memory of 10 images per class from the previous tasks. And when we are training the new task 2 and 3, for example, we learn from those new digits and also from the 10 pictures of each of the previous classes that we have stored. So for this simple example, GEM also works very well at maintaining the performance on the old tasks. The two that don't work in this case is just plain EWC. So plain EWC falls back to 0 performance very quickly. And also a control for our method, which is what if we had those biases, but instead of using this fast gradient sign direction to train them, we just train them like regular units just using gradient descent. And so if we do that, we find that the performance also falls off very rapidly. So this basically tells us that there is something special about doing this training with the fast gradient sign direction, as opposed to just adding a few units, and maybe the extra degrees of freedom from those few units are the ones that are responsible for the maintained performance. Here we find that this is not the case, because here we added those extra units, but if we just train them like regular units, they don't help with the performance. So the same pattern is repeated for the subsequent tasks. So here, as we start learning task 2, all the methods are able to learn it very well. But as soon as we switch to task 3, at this transition here, both EWC and GD plus EWC also fall to 0, while GEM and BD plus EWC are maintaining the performance. Likewise for task 3, task 4, task 5. All right, so this was on incremental MNIST, which is fairly simple. We can repeat the same experiments on incremental CVPR10. We get basically the same results. If we go to a little bit more complex incremental CVPR100, now we are starting to lose GEM, at least if we are still doing it with only 10 images per class. If we increase that number to 256 images per class, GEM can still maintain the performance. However, this now requires a lot of extra storage just to store those 256 images for each of the classes of each of the previous tasks. Here is a comparison for this. So here we are just looking at the additional memory that is required for each of the methods. For the beneficial biases plus EWC, again, this was with a small multi-layer perception. We only required 4.8 kilobytes just to store the values of those biases. In comparison with GEM, storing 10 images for each class amounts to about 47 kilobytes that needs to be stored for that incremental MNIST. Things get much worse if we look at GEM 256. Now suddenly we need to store, almost 1,000 times more data using GEM than we would using our BD plus EWC method. Note that the one that performed the best on incremental CFAR 100 was when we combine our beneficial direction plus PSP, which is one of those context matrices kind of approaches. So there is a little bit of extra cost here just to learn and to store those context masks, but it's still very small compared to, for example, rehearsal methods like GEM. And the performance is still better. Here is a more complex data set. So this is going to be the final test for this method. So this is a sequence of 8 data sets where each one is actually quite complex. So we start with a flower data set, which has 102 classes of flowers. And that's going to be just task 1. Okay, so in task 1, we learn to discriminate roses versus lilies versus daisies, petunias, and you name it. Okay, so that's going to be task 1. And once this is learned, we are going to now switch to task 2, which is going to be 67 classes of scenes, like bedrooms versus kitchens versus restaurant versus gas station, and so on. We then switch to 200 classes of birds. So this is going to be task 3. And then 196 classes of cars, aircraft, action, letters, and SVHN, which is the house street numbers filmed by Google Street View. So here, as you can see, the total number of classes that we are going to learn is 717 over all of those tasks. So this is a significantly more challenging problem than what we have done with just a little MNIST or CFAR10. So here we are looking at different methods, some of them that I've not described yet, but that are quite popular in the literature. And the main comparison for us is what if we start with, for example, EWC, which only gets about 50% correct on average over all the tasks here, and then add our beneficial biases to this. We can see that that gives rise to an improvement of about 2.8% in the overall performance. The best performer here, so before us, was PSP, which is again one of those context matrices methods, and it was reaching the state of the art on this data set, and we can then beat that by adding our beneficial perturbations on top of that, and then getting the new state of the art performance. All right, so this method is working quite well, and the cost is very low. The cost during training is very low because we are basically just reusing the gradients that are already computed to do the regular training of the network. And the storage cost is also very low because, again, there are usually a very small number of neurons and hence a very small number of biases compared to the number of weights that there is in the network. So I will show you now an application of this, which is that we can use the same idea to create adversarial robustness. So you are all familiar, I'm sure, with adversarial attacks in which we can take a picture that is correctly classified by a network and add some very carefully computed noise to that picture to force the network into misclassification. And this noise is not random at all, right? It's computed from an analysis of what is the difference between panda and gibbon as far as the network is concerned, and then choosing the values here in that noise image so as to basically cross over from the panda decision region to the gibbon decision region. Even so, that noise may not be perceptible to the human eye. It will have some significant effect on the internal computations in the network. So perhaps the easiest way, and maybe one of the most popular ways these days to combat those adversarial attacks is to do so-called adversarial training. So this works as follows. We start with a data set that we are going to call a clean data set at this point. Train a network. Once the network is trained, we can use a gradient extractor and basically compute adversarial attacks. We compute those adversarial attacks and we can apply them to the whole data set and create a whole new data set of adversarially attacked training images. Okay, we can then combine this with the clean examples and retrain the network so that now we have basically preempted the attacks by thinking about them even during training time, and then retraining the network on a combination of the unattacked and attacked pictures. And hopefully now the network is going to be more robust to those adversarial attacks. So this works great. It's just very expensive because we need to train the network a first time, then we need to create and store that whole data set, which takes a lot of memory. And then we need to train the network a second time using both the clean and the adversarial examples. So the cost of doing this is actually very expensive. So we thought that maybe we can use the same idea as what I've shown you for lifelong learning, but now not in the context of lifelong learning anymore, but in the context of trying to create robustness against adversarial attacks. So the basic idea is that we are going to do the same thing as what we have done, which is, so in our case, we are going to just consider those clean training examples, and we are going to train a BPN network using those. So that means the clean examples are going to be used to train the network, and we are going to train the weights of the network just using gradient descent as usual. And in addition to that, we are going to train those biases using the fast gradient sign direction. And we are then going to have a network which has not only its weights trained in the conventional way, but also its biases that have been trained using this fast gradient sign direction method. And the idea here is that basically we hope that we are approximating the same process as what is being done here, but we have completely bypassed the need for creating those actual pictures with the actual adversarial attacks in there. We are basically just, if you want, imagining what would happen if we were doing an adversarial attack and then computing the beneficial biases that are going to counteract those adversarial attacks. So let's see how well it works. First of all, the cost of this is very inexpensive. So here we are using a ResNet 50. In terms of forward flops, it's exactly the same because that network already has biases. Just here we are training them in a different way. But when we are doing the forward pass, the biases are still going to be applied, both in the classic network and in the BPN version of it. Now the backward pass is a little bit higher cost, and this is just so that we can compute those fast gradient side direction in order to train the value for all those biases. All right, here are the main results. So here we have trained a network on clean examples only, and we are going to test on clean examples and on adversarial examples. So this is going to be testing on clean examples and here testing on adversarial examples for both BPN, which is our approach, and the classical network. So remember that we trained on clean examples only. So when we test on clean examples, the classical networks is performing very well, and BPN is also performing very well. Now, when we test on adversarial example, the classical network is performing very poorly, meaning it has been deceived, if you want, by the adversarial attack. And this is expected because this network has not been exposed to adversarial examples before. However, just our network has not been exposed to adversarial examples either, right? We just imagined them during training. And you can see that that was enough to become robust to those adversarial attacks when they actually do occur in the images. So again, during the training of BPN, we never instantiated an attack. We never created adversarially perturbed images with the noise added to the images and so on. We never use that. We just imagine those in order to set the bias values. And now when we see an attack for the first time, we are still robust to that attack. So this was for MNIST on LeNet, and here are some other results. They are not all as good, but overall they show greater robustness to adversarial attacks than what you would have by just doing classical training. One last question that we wanted to ask about this is whether we would create some robustness to other attack methods. So here we have used the fast gradient sign direction to train the bias values, and maybe that will render us, resilient to some kind of attacks, but maybe not to other kinds of attacks. So here we tried a number of different attacks. So again, the fast gradient sign direction was always used during training, but now during testing, we're here trying 4 different types of attacks. So as you can see, the approach is robust to some attacks. It's not robust to all attacks. For example, this one still gives rise to a poor performance overall on the both MNIST and Tiny ImageNet. However, that performance is still better for BPN than it is for the classical network. And likewise here, the performance is very poor, but still better for BPN than for the classical network. So overall, what this means is that even so we use the fast gradient sign direction to set the biases, that gives rise to some, somewhat generalized resilience to a number of different adversarial attacks at test time. All right, let me switch gear now to a different project, which I thought would also interest you, because it has to do with training of networks on sequential data. And that sequential data is going to be neural recordings from brain implants that are used in biomedical prosthetics, like artificial limbs and these kind of things. So the setup is going to be that we are going to have experimental data that is recorded from monkeys. And the monkeys are performing a reach to target task in which they are looking at a computer screen, and a red square can appear at any location on that screen. And using this manipulandum, they are going to make a reaching movement in which they are basically trying to move that cursor towards the location of the target. So when they do that, we record the kinematics of the movement, which is going to be in terms of position X and Y, velocity X and Y, acceleration X and Y of that manipulator. And we also have an electrode array that is implanted in their primary motor cortex that is going to record neuronal spiking activity from about 70 neurons. So here we have about 70 neurons. Each one is going to be a row of data here, and we are going to record their activity over time. And this activity is going to be in terms of action potential. So each time a neuron fires, we are going to get a little dot here in one of those traces. So each trial where the monkey reaches for one of those targets is going to give rise to one of those raster plots here of neural data. So when we develop prosthetics, which is basically to help people, for example, who have had spinal cord injury and they cannot move their arm anymore, so we want to develop a brain implant that will read out signals from their motor cortex and then later on potentially activate a robotic arm. The way in which we do that is by training a so-called LSTM BCI decoder. So the BCI decoder is the brain-computer interface decoder, and using an LSTM is currently the state of the art for those decoders. And the way those decoders are trained is that we give them some of the recorded neural data from the electrode array, and we give them ground truth kinematics for what the movement was that the monkey operated while we recorded those neural spikes. The BCI decoder is from the neural data is outputting its own set of kinematics, and then we can just apply a loss between the output kinematics and the ground truth kinematics in order to train that decoder. Okay. So the question that we are going to address is how can we train those decoders better? And is there anything that we can do? And what we are going to be looking at is, can we do some kind of data augmentation in this spiking domain, which is something that has not been done before. We are going to do that in order to try to address two questions. How can we adapt the trained decoder to either a new session or a new subject? So why do we need to adapt to a new session? That's because so those electrode arrays, they get implanted chronically, so long-term, and basically they are going to change and evolve over time. Either the array may move a little bit just because of pulsations of arteries nearby, or there is carrying tissue that may develop around some of the electrodes. So from one day to another, you may not have exactly the same neurons that you are recording from. Some electrodes may be deactivated over time, and so on. So what this means is that currently, if you are a patient implanted with one of those arrays, you have to retrain your BCI decoder pretty much every morning before your prosthetic limb can operate correctly. So that's the first question that we want to address. Is there any way we could accelerate this or minimize the amount of retraining that is necessary every morning for those patients? The second is, could we leverage some of the training that we may obtain from one subject in order to facilitate the training for another subject? And the reason for this is that training data is very expensive. And so maybe we can try to minimize the amount of retraining that will be required when we go from one subject to another. All right, so very briefly, the method works as follows. We are going to train a GAN, and it's going to be for the first time a GAN that operates in the space of spike trains. So this GAN is going to take kinematics as an input plus some noise seed, like is usually the case with GANs, and it will generate synthesized spike trains that resemble the real spike trains that one would have recorded when the monkey was operating those kinematics. And this GAN is going to be split into two parts: a generator, which is going to be a bidirectional LSTM, and this one will give rise to some kind of internal representation, and a readout module that is going to take that internal representation and output some well-formed spike trains with the right kind of low-level statistics that we expect. So once we have trained this generator, we are then going to use it to try to do this smart data augmentation. So to do that, we are going to first record a little bit of real data. So when we switch to a new session or to a new subject, we are still going to need to record a little bit of real data. And that real data is going to be used to fine-tune that readout module, either to a new session or to a new subject. The bidirectional LSTM is going to be kept frozen, so we are not retraining that one. Once we have fine-tuned those guys, we can then generate as much synthetic data as we want using the GAN from any kind of real kinematics that you may want. So because we have this ability now of generating a lot of realistic looking neural data for either the new session or the new subject, we can now combine that with a little bit of real data that we obtain from this session or that subject. We're actually going to use the same real data that we used for the fine-tuning and combine that little bit of real data with a lot of synthetic data and then retrain our BCI decoder for that new session or that new subject. Okay. So the idea is, again, to use this GAN that is fine-tuned to a new session or a new subject to generate a lot more additional data that will help with retraining the BCI decoder. All right, let me skip this. This is just some sanity checks on how well the model is working. let me just show you the main results. So here we are looking at when we do cross-session training, how much time, how much training data would we need to record on a new session. And we are going to compare real only, which is if we just record new and start from scratch training the BCI decoder. So we will need on the order of 13 minutes of data in order to successfully train that BCI decoder. And here you can see this is compared to the best achievable performance, looking at how many minutes of training data we get, and how much below the best achievable performance we are. So first of all, with real data, if we are only using real data for training, we need at least on the order of 5 minutes for the BCI decoder to even converge, but then the performance is not so great. And by the time we get to 12, 13 minutes, we are getting a good performance. So this is just using real data. Now we can compare that to our approach, which is going to be that one, where we basically only record on the order of 2 minutes of real data, and then use our GAN to generate a lot more. So first we are going to fine tune the readout module, right, using this data, and then use the GAN to generate a lot more additional synthetic data. Let's say, for example, 10 minutes in this case. So at the end, we still train with 12 or 13 minutes, but only about 2 of those are real. And when we do that, we now achieve also close to the best achievable performance. Actually, we achieve the best achievable performance, which is the one that is not shown in this graph here. We can compare this to other approaches. So instead of using this GAN, we could do other things like more standard data augmentation methods, for example, with mutation, just concatenating snippets of real data in random order, or doing various kinds of stretching, just like we do in a standard data augmentation. So those methods help to some extent, but are still not as effective as this GAN-based data augmentation. For cross-subject, it works essentially the same. So we have the same kind of reduction here, that when we take our decoder and want to train it on a new subject, it would require 8.6 minutes of real data only, but only a very small amount of real data is necessary to fine-tune the readout module to the new subject, and then basically the decoder can be trained using all synthetic data pretty much. All right, in conclusion, I've shown you 2 different projects. One developed new beneficial biases that are helpful not only with lifelong learning problems, but also with developing robustness to adversarial attacks. I believe there is a lot of promise in this approach, and it's quite different from what has been proposed before. So I invite you to look at it in more detail if you're interested. And the second project, we looked now at how to increase the robustness of brain-computer interfaces that are using sequential data, in this case, neural spike trains. And we found that we can create for the first time a GAN that is operating in the spike domain. And we can use that to greatly accelerate the learning of brain-computer interface decoders. And allow them for the first time to be transfer cross-session and cross-subjects. So thank you again for this. I would like to thank my sponsors, and I'm ready to take any questions. Thank you.